Hello students, welcome to this lecture in which we continue doing surface integrals, but now we would like to use our old xy coordinates or xz or yz instead of u and v. That's the goal for this lecture, but so let's try to set it up. So in the case where our sigma is a surface given by an R function, surface of the form z equals to g of xy. What we can do, we can take x to be equal to u and y equal to v. So instead of u and v, we can use x and y. And and we can write the equation of the surface as, didn't spell it right, of the surface as R equal u, where u plays the role of x, plus v, which plays the role of y. And since z is equal to g of xy, we can put it here, g of xy k. All right, so then what we can receive for the partial of r with respect to u. The partial of r with respect to u will be, so x here it should be u and y here should be v. I have to finish it off because we call x to be u and y to be v. So dr du will be 1I, so it's 1, then 0, no u here, and then we'll have dg du. And then dr with respect to v will be 0, 1 dg dv. So what we need to calculate now, we need to calculate the cross product between dr du and dr dv. So we have I, j, and k. All right, so for the first one, we have 1, 0, dg du, then 0, 1, dg dv. So for the I component, we're going to get 0 times this minus 1 times this, so this is dg du with the minus sign, I, minus, then for the second component, it's going to be 1 times dg dv and then 0 times dg du, so it's going to be negative dg dv j plus 1 times 1 k, so this. Also, we need to calculate the magnitude of this vector, so it's dr du cross dr dv, which is the square root of this term squared, so it's dg du quantity squared plus then this quantity squared is dg dv quantity squared. Okay, and then 1 squared. But remember, u is x and v is y, so it's the same as saying that this is d, and g is z, right? G is z. G is a z function. So basically it's the same as saying dz dx, dz dx quantity squared plus dz dy quantity squared plus 1 squared. So what does it tell us? It tells us that if we want to find the integral over sigma of f, x, y, and z ds, that's going to be the integral over the region of f of x, y, but instead of z we can put g of x, y. And at the end we're going to put a square root of dz dx squared plus dz dy squared plus 1, and at the end we have dA now. Alright, so the question is what is the region R? That's the only question remains. So the region R lies in the xy plane, because the parameters are x and y, because the parameters are x and y. So the only thing to discuss is what is it geometrically. Geometrically, the region R is the projection, of sigma on the xy plane. All right, so let's try to put it as a theorem. So the theorem tells us the following. The theorem tells us that let sigma be a surface with equation z equals to g of xy, and let R be its projection on the xy plane. Then if G is if G has continuous first partial derivatives on the region R, and f of x, y, and z is continuous on sigma, then we can rewrite our integral in the nice form that tells you that double integral over sigma of f, x, y, and z ds is equal to the double integral over R of f of x, y, g of x, y, and we put a square root here where we say dz dx quantity squared plus dz dy quantity squared plus 1 dA. Right? And the same thing we can rewrite if we do the projection on any other plane. On any other plane, it would be the same. We can write it a couple more times if we want to. So how would it look for the other planes? For the other planes, this would be so let's say this is part A of the theorem. Part A. All right, so if we put it here, sorry, put it here as part B. So let sigma be surface with equation we have z equals, but now let's think in terms of y. So it's y. Then here we'll have x and z, and let R be its projection on the xz plane. So this should be xz plane. If G has continuous first partial, is continuous on sigma, then f of xyz integral. So instead of y here, instead of y, we're going to put g of x and z, and here we're going to put z, then the first derivative with x, second derivative with z, and that would be our answer. So we use xz plane for the projection. But also we can use yz plane as a projection. So if we take our rule and we think of part C, and this is a surface, so over here equation will be x equals, right? Equation will be x equals. So x equals to y and z, and instead of xy plane, it's going to be yz plane. Yz plane. All right, so over here we have to, instead of x, we have to put g. So g of y and z, and this is y, and this is z, but nothing else changes. So we can project it on any plane we like. Okay, so let's try to do some exercises. So first example would be like this. Evaluate the surface integral of xz ds over sigma, where sigma is the part of the plane x plus y plus z equals to 1 that lies in the first octant. All right, so what does it mean geometrically? Geometrically, we have x positive, y positive, and z positive. So that's the first octant, because we have 8 different parts for the 3D space. So if this is x, this is y, and this is z, if we take both x and y to be 0, so it's going to be 1 on the z-axis. If we take y and z equals, x will be equal to 1, and z will be equal, and y also going to be equal to 1. So we have this plane that it's an inclined plane, and so we're doing the integral along this on this plane. This is x plus y plus z equals to 1. Okay, so this point here is 1, 0, 0. This point over here is 0, 0, 1. And this point over here is 0, 1, 0. All right, so we set it up. So let's start moving forward. So we'll say that we need z equal to the function g of x and y. So basically, we have to solve for z. So is it easy to solve for z? Yes, we can say that z equals 1 minus x minus y, and this will be our function g. Right, so this is our function g over here. And our f function of x, y, and z is equal to x times z. All right, so now we need what? We need to calculate dz dx. It's going to be just -1. We need to calculate dz dy, which is -1. So that means our integral over sigma of xz ds is equal to integral over the region R, here. And so what? We keep x as x, but for z we put the value, which is 1 minus x minus y. And we have a square root of -1 squared plus -1 squared plus 1 dA. The only thing left for us is to figure out the projection of this plane onto the xy plane. So the projection, so if we look from the top, then our projection on the bottom will be this triangle over here, So basically, just trying to fill it out. So this triangle in green on the bottom is our R region. This is our region R. All right, maybe not the best color, but I picked it by random. Okay, so let's try to figure out this region in xy plane. So we redraw it in xy plane to figure out the region. So let's think. On the y-axis we go all the way to 1. On the x-axis we go all the way to 1. So we need to figure out this line over here. And this line has a -1 as a slope, right? And y-intercept is 1. So what does it mean for us? -1 times x plus 1, right? So -x plus 1 is our line. This is our line, -x plus 1. At 0 it's 1, at 1 it's 0, so this is the line that is of interest for us. Okay, so we figure it out. So we move forward then. We say equal, we say the integral, we say for the, then we have to choose any particular value x. For any particular value x, y goes between 0 and this line. So between 0 and minus x plus 1 of, and we multiply it out, so we get this expression, and this will be square root of 3, so we can put it up front here. And we have dy, we have dx. And y is first because we fixed x. The only thing left is to put the values for x, 0 and 1. So we do this out, we get the integral, or we have square root of 3. We have square root of 3, we have the integral from 0 to 1 of, so first with respect to y, so it's xy minus x squared y minus xy squared over 2 from 0 to minus x plus 1 dx. So we did this out. Next thing is to move forward and plug everything in. So we still have square root of 3. We still have integral from 0 to 1. So we have x times minus x plus 1 minus x squared times minus x plus 1 minus x times minus x plus 1 quantity squared over 2. And if we plug in 0, it will zero everything out. Alright, so we have gotten this expression here. What is the best way to simplify it? I'm not 100% sure. Maybe we'll do it here on the side. So let's try to simplify it. So what I'm going to do, I'm going to probably factor this x so it wouldn't bother me. Then I'll have negative x plus 1. Then I'll have minus x times minus x is positive x squared. And minus x times 1 is minus x. Okay, and then what do we have? We have this expression squared. So 1 minus x squared is going to give us x squared minus 2x so this will be plus, this will be minus. Oh, I'll keep minus here, I'm sorry. I'll write it in parentheses. So this will be minus 2x, this is going to be 1, and on the bottom we have 2. And I factored one of the x's out. Alright, so what do we have? We have x times negative x, and negative x is negative 2x. Alright, negative 2x. So then we have 1, we have x squared. Then this minus we distribute through, so it's negative x squared over 2 plus 2 and 2 goes away plus x, and minus 1/2. So let's see, we have negative 2x and x, so one of them goes away. Then we have 1, so we have negative x left. 1 and negative 1/2 is 1/2. And then we have x squared minus x squared, so it's x squared over 2. So we go back, we put it over here, so we have 0 to 1, and multiply by x, so it's negative x squared plus x over 2 plus x cubed over 2 dx. And so we have square root of 3. Then minus x squared over x cubed, over 3 plus x squared over 4 plus x to the 4 over 8 evaluated from 0 to 1. So finally, when we plug in 1, we get negative 1/3 plus 1/4 plus 1/8 and dot dot dot. I'm not going to do that, but it's clear, right? That's our answer. Alright, so we were able to do this example. We move to the next one. So to make things a little bit more complicated. So the assignment says evaluate this double integral over sigma of y squared z squared ds, where the sigma is the part of the cone z equals to square root of x squared plus y squared that lies between the planes z equals to 1 and z equals to 2. So graphically what this means, if we fix z, this will be concentric circles, right? This would be concentric circles centered at 0, and radius will be the square root of radius will be z. So basically, if we think about z plane going through 1, so this would be the plane something like this. Okay, so in this plane, when z is equal to 1, the radius of a circle is equal to 1. So we have a circle with radius 1 over here. Okay, so that's what it means for us. And then when we have a surface z equals to 2, suppose this is 2 and this is 1 here. Right, so what happens at 2? At 2 our plane goes over here. So the radius will be 2, so we'll have a bigger circle. Doesn't want to understand my drawings. All right, so I have a bigger circle here. And so if we connect this, so we have a lot of concentric circles go around like this. All right, so I have a bunch of concentric circles. All right, so there are a bunch of them. So it creates this 3D piece. All right, so we already have a z function equal to g of x and y, which is the square root of x squared plus y squared. And we have f of x, y, and z equals to y squared, z squared. So the couple of things left to calculate is dz dx, dz dx. So it's going to be 1 over 2 square root of x squared plus y squared. And we have to multiply by the derivative of the inside, so it's going to be 2x. So 2 and 2 goes away, and we get x over the square root of x squared plus y squared. And by symmetry, dz dy will have the same answer, so we don't really need to evaluate it. We just write y on top. All right. So we figure these things out. So that means what? That means that we'll have a square root of dz dx squared plus dz dy squared plus 1 equal to, let's try to see what we're going to get. So first one squared, so it's x squared over x squared plus y squared plus y squared over x squared plus y squared plus 1. But we can clearly see that if we add these two terms, numerator will be x squared plus y squared over x squared plus y squared plus 1. And so we have square root of 1 plus 1, which is a square root of 2. Square root of 2. All right. So now we're ready to set it up. So we say that the double integral over sigma of y squared z squared ds is equal to the integral over the region R, which we'll figure out in the future. So we keep the y squared untouched, and for z we put our expression, so it's going to be square root of x squared plus y squared squared, and then we have square root of 2 dA. So the only thing left for us to figure out is projection of this surface, the projection of this surface. So I will redraw it a little bit. So I'll put my x over here like this, then y over here like this, and z going up. So basically on the bottom we have a small circle, and on the top we have a big circle. And if we take a look from the top, on the bottom we just have to trace this big circle on the bottom, right? Big circle on the bottom. And this small circle also we have to trace. So for the small circle, we're going to have a circle of radius 1 in xy plane. And for the big circle, we have a circle of radius 2 in the xy plane. So basically, if we look from the top, we see something like this. We see big circle. We see big circle, but inside of the big circle, we see a small circle. All right, and this is the center over here. So our region is this region over here that fills up everything except this middle little circle. So between circle of radius equal to 2 and radius equal to 1. Okay, that's what we have. That's our projection. So how we can describe this R? This R we can describe as annulus, right? So R is annulus enclosed between circle of radius 1, which is x squared plus y squared equals to 1, and circle of radius 2, which is x squared plus y squared, I said 2. That's not really right, but the radius is 2, but x squared plus y squared radius has to be squared, so it has to be 2 squared, which is 4, right? Okay, so circle, circle, conclusion, polar coordinates. Okay, so we use polar coordinates. So let's go. So we have integral of y squared. All right, and polar coordinates means y equals r sine of theta, x equals r cosine of theta, and our theta is between 0 and 2 pi, and our r is between 1 and 2. All right, so we have the integral over the sigma of y squared z squared ds now becomes, so we use this one over here. So for y we're going to put r squared sine squared of theta. Then for the square root squared is just x squared plus y squared, but we know that x squared plus y squared is going to be equal to r, right? Why is that? Because x is r squared cosine squared of theta, and y squared is r squared sine squared of theta, so we're going to get r squared. So it's going to be r squared. So we put it over here. And as you remember, for If we switch to polar coordinates, we have to introduce extra r, dr d theta, and our r changes from 1 to 2, and our theta changes from 0 to 2 pi. And we also have a square root. Square root of 2, I forgot the square root of 2, remember. If we go back, we have this square root of 2. Alright, so it should be square root of 2, and for dA, r dr d theta. R dr d theta. And I don't really write product signs. So let's try to think about it. We take square root of 2, we put it outside. And so we rewrite 0 to 2 pi, then 1 to 2. So let's try to calculate this. We have r squared, and r, so it's r to the 5. And we have sine squared of theta, dr d theta. So continue on, square root of 2, integral from 0 to pi, then antiderivative of r to the 5 is r to the 6 over 6, evaluated from 1 to 2, and we have d theta left, and we have, forgot the sign. We have sine squared of theta d theta. So let's plug in 2 over here, 2 to the 6. What's 2 to the 6? 2 to the 6 is right. 2 to the, so 2 to the 5 is got stuck. It's 32, right? It's 32. So we get 32 over here for the 6, right? So we'll get what? We'll get sorry, a little bit of technical issues. So we're calculating r to the 6 over 6, so we plug in 2. So it's what? 2, 4, 8, 16, 32, 64, right? 64. So square root of 2, integral from 0 to 2 pi, we have 64 minus 1 over 6 sine squared of theta d theta. Alright, so that's going to be 63 over 6. 63 over 6. So here we'll do it on the side. 63 over 6, so we can divide by 3. Divide by 3. So this will be 2 and this will be 21. Alright, so we get square root of 2 divided by 2, which is this 2, and then 21 in the numerator. So we put this outside of the integral, and the integral goes from 0 to 2 pi of sine squared of theta d theta. And again, we've done this integral a couple of times for the sine squared of theta d theta. The formula that I'm going to use, the formula says that antiderivative of sine squared of x dx is equal to x over 2 minus sine of 2x over 4 plus c. So that means square root of 2 over 2, we have a 21, and we have x over 2 theta over 2 minus sine of 2 theta over 4, evaluated from 0 to 2 pi. And this is the formula that we used for this integration. So finally we plug everything in, we get 2 pi over 2, so it's pi, minus sine of 4 pi is 0, so it's minus 0, and then if we plug in 0, this will be 0, and sine of 0 is also 0, so minus 0. So final answer is 21 over 2 times square root of 2 pi. And that's our answer for this exercise. And the last exercise for this lecture, the last exercise is going to be, can we use this idea to find the mass? So suppose that a curved lamina sigma has a density delta of x, y, and z equals to some delta sub 0, some constant. So it's a constant density. And it's a portion of the paraboloid z equals to x squared plus y squared below the plane z equals to 1. Below the plane z equals to 1. And the equation is to find the mass. So find the mass of the lamina. All right, so let's start building it up. So we know that z equals g of xy is equal to x squared plus y squared. So it's a paraboloid. What does it mean? Paraboloid means that we take a parabola pretty much, and in every direction it's going to be a parabola. So paraboloid looks like this. It starts at 0, 0, and in every direction we have a parabola. Okay, so we have a paraboloid, something like this, and we have a plane here, plane over here, which is z equals to 1. So over here on the top, maybe I'll do the plane later. So over here on the top we have a circle, right? So if we okay. All right, so this is my paraboloid. Again, it's cut off by a plane z equals to 1. All right, so this is the plane z, sorry. Z equals to 1. This is a plane z equals to 1, and the paraboloid is described by x squared plus y squared. Okay, so we have our function z, then that means dz dx is 2x, dz dy is 2y, and to find the mass, we have to take the integral over the density, and our density is delta sub 0 ds. And we know that it's going to be the double integral over the region that we will discuss shortly. Then we have 2x squared plus 2y squared plus 1 squared dA. Okay. And so basically we need to calculate this integral, because this is a fixed one, so we can fixed density, we can move it outside, and it's going to be 4x squared plus 4y squared plus 1 dA. That's what it's going to be. Now we need to figure out the region. So let's look at the region. So if we look from the top, we just have to trace this circle over here. All right, and then that means on the bottom we have a circle of this radius over here. And we know that over here z is equal to 1, so this circle will be 1 for z equals to x squared plus y squared if we square both sides. This would be our circle if we look from the top. So we move on. So we say mass is equal to, so we have the density up front, which is a fixed number. Then probably again polar coordinates are good. It would be good to have polar coordinates over here. So in polar coordinates we'll have a square root. Remember, 4x squared plus 4y squared is just going to be, and since r is equal to 1, since r is not equal to 1, since we have x equal to r cosine of theta and y equals to r sine of theta, then we'll have 4r squared cosine squared of theta plus 4r squared sine squared of theta plus 1 dA. And our r goes from 0 to 1, 0 to 1, and the angle goes from 0 to 2 pi for theta. And here, instead of dA, we're going to write r dr d theta. Okay, so we know that these two terms together will just give us 4r squared. So it's going to be delta sub 0 integral from 0 to 2 pi square root of 4r squared plus 1, because this is just 4r squared and 1 comes down. We have r dr d theta, r dr d theta. Okay, so standard U substitution to find this integral. So let's find it on the side. Integral of 4r squared plus 1 r dr. So we'll say U is equal to 4r squared plus 1. Then differential of U is 8r dr. And then dr is du divided by 8r. So integral becomes u to the 1/2 r, and instead of dr we put du over 8r. Right. Okay, so let's do this out. So r and r goes away, so we have 1 over 8 u to the 3 halves over 3 halves, so it's times 2/3, and our u is 4r squared plus 1. So we have 4r squared plus 1 to the 3 halves, and 2 and 8 gives us 4 on the bottom, and 4 times 3 is 12. So we get 1/12 times this expression, which we put back over here. Right, and the integral from 0 to 1, So we have integral from 0 to 2 pi of this, we get delta sub 0, we have 1 over 12, 4r squared plus 1 to the 3 halves evaluated from 0 to 1 d theta. Okay, so I'll put this in a box, our extra calculations here. So it's equal to and we take 1 over 12 and move it outside, and we plug in 1, so it's going to be 4 times 1 squared plus 1, so it's 5 to the 3 halves. 5 to the 3 halves, and then if we plug in 0, it's going to be 1 to the 3 halves, which is 1. So delta over 12, integral from 0 to 2 pi, one more time, 1 is going to be 5 to the 3 halves, 5 to the 3 halves, and if we plug in 0, this will be 0, so it's 1 to the 3 halves, which is 1. So it's minus 1 d theta. Okay, so basically what do we have? We have delta sub 0 over 12, 5 to the 3 halves minus 1, and theta evaluated from 0 to 2 pi. And if we look into the future, 0 will zero everything out, so the only thing we need to plug in is 2 pi. So we have 5 to the 3 halves minus 1 times 2 pi, so we can divide, and we have delta sub 0 pi divided by 6, 5 to the 3 halves minus 1. And that completes this lecture about surface integrals. Alright, and I'll see you in the next lecture.